Hello. Time to talk about the last chapter of modern physics, and that's nuclear physics. We're going to talk about radioactivity as well in today's session. Very interesting one. All of this with me, your favorite captain, your navigator, and your master teacher at Vedantu going live. How is everybody doing? I hope you are doing all fine. Welcome aboard. Let me just quickly guide you what we are going to do in this session today. This is a part of the Pathfinder series, which is a long-term course for free on YouTube in English medium for all the aspirants preparing for competitive examinations. So we are coming towards the end of the Pathfinder series. Thank you for tuning in for all this while. And yes, in today's session, talking about nucleus, the radius, the components of nucleus, nuclear forces, binding energy, the graphs, and yes, going to fusion as well as fission, and then the radioactive particles and the laws of radioactive decay, along with half-lives and average life. All of this in today's session. So here's your first quiz coming up on your screen. Hi Sneha, Akash, Captain, America, Ankit, Neville, welcome Ramya, hi Kunal, hello Jessica, hello Syed Wazim. And guys, I hope you have seen my information on the board's announcement. If you have not seen it, please watch it. It's hardly going to take you 2 minutes. Go ahead, check it out. Most important notification has been announced, and the breaking announcement first happened on your favorite channel, JEE Enthuse. So that's the reason why you should go ahead, smash the like button as well as hit the subscribe button. So let's see what you guys say about this. Akshay Murgan, regarding NEET, I'm predicting it should happen only after May. Maybe May end or June, somewhere around that. Maybe you can take it probably like June would be a safe time to assume it. Okay, Ankit saying A. What about others? Hi Gautam. What do you guys say? Ankit is already battle ready. Is there any reason for the answer? Is there any reason for the answer of the question? Well, yes, you will get to know the reason for the answer of this question. The correct answer is nucleons. Nucleons. Yes, Ramya, you got it right. Your favorite chapter, of course. The mass number, atomic mass number, is equal to the number of, is the way it has been defined. Atomic number is different, atomic mass number is different. Nucleons means all the particles inside the nucleus are called as nucleons. What kind of particles are there inside the nucleus? Come on, put it up in the chat box. What kind of particles are there, or what do you think nucleons are? Just put it up in the chat box. Let's see how many of you know this. And well, I hope you know me. And in case you do not know me, you know what you should do. Go, first of all, go to Instagram. You can follow me over there. You can get to know more about me. But yes, that's my quick intro slide. Very good. Protons plus neutrons is nucleons. Perfecto. Amazingo. And yes, have you already smashed the like button, subscribe button? Have I given you enough reasons to join the channel? All announcement, everything happens on this channel really quick. Fatafat. So go ahead. Join it right now in case you are not a member. Promote the channel. Make sure all your friends, your schoolmates, classmates, relatives, friends, cousins, everybody should be on this channel. That's how we are going to get the energy. So last year we had amazing breaking records where more than 1,500 students cracked JEE Advanced. Thousands of them cracked JEE Mains from Vedantu. And this year is not going to be different. And you guys have made a promise to all of me, like all of us out here, that you guys are going to do exceptionally well. You guys are going to nail it. And I know you guys are going to keep your word. And I'm going to keep my word by giving you all the content that is necessary on YouTube and as well as on the platform. So yes, Vedantu is committed to give you all kinds of courses on the platform as well as on YouTube. Make sure you check them out. Make sure you join the channel as well as the crash courses running right now. All right, so let's get started with this chapter. The CBSE site is most likely not opening because, you know, many students will be trying to log into it. So probably it has crashed. Good evening, Nikhil. All right. So like we all have just agreed upon, and what's a nucleus made of? Nucleons. Nucleons is nothing but protons and neutrons. Protons are positively charged, neutrons neutral, no charge as such. Nucleus is very small as compared to the atom. It's very dense. the electrons are very light and they revolve around the nucleus at very far away distances. So the nucleus is a small condensed body which is at the center of the atom, and you should know these important data points, especially regarding neutrons and protons. Mass of a neutron is of the order of 10 to the power minus 27 kg. You need not remember all these digits. It's not necessary, it will be given to you. But you should know it is roughly 1.6 into 10 to the power minus 27. That's how small the mass of the neutron is. Proton's mass is also very similar. Obviously, it is positively charged. It's roughly similar, small difference in the digits on the third or fourth decimals. So 10 to the power minus 27 kg, of course. Yep, Akshay, modern physics will be completed today. The semiconductors, etc. will be done, day after tomorrow and so on and so forth. So some people include that as well in modern physics, but yeah, it's up to you how you want to call it. Okay, so let's move ahead with the next part, which is the atomic mass number and atomic number and all these things. How do you represent in nuclear physics any element? Any element, whenever you want to represent it, you generally try to give in all the details of how many protons, how many neutrons are there inside the nucleus, and this is how you represented it. X stands for which element you are talking about. Hydrogen, helium, lithium, I don't know, it could be anything. Z is your atomic number. Okay, let me just get it over here. So this X is your element. This X is your element. This Z, of course, is your atomic number. But remember, this A is atomic mass number. Both are different things. And this also means A, which is the atomic mass number, is Z, which is the number of protons, plus the number of neutrons. So keep this in mind, very, very straightforward. This will tell you always the number of protons which are there. This will always tell you the number of neutrons which are there. And together, this will tell you the number of nucleons which are there inside the nucleus. Very good. Excelente. Yes, Veera Gava Reddy Kotapalli. I will be teaching you semiconductors right from basics. Like the Pathfinder series promises you. I have promised you that I will be teaching everything in detail. The entire course is available for you. The entire physics course is available for you in the Pathfinder playlist. Please make sure you check it out. Semiconductors, everything done in detail, just like I have done modern physics and any other chapter. So, having said that, there is a new unit which you need to know regarding mass. See, the mass of a proton or a neutron is so small, it's not convenient to deal with such small numbers. So I define a new unit for mass. So what's that new unit for mass, my warriors? The new unit, you would have learned this in chemistry. What is it? 1 AMU. AMU. Yep. So 1 AMU is 1 by 12 mass of an atom of C12. That is what it is. I hope this is clear. Yep. So yes, I'll take from lecture 1, obviously, Veera Gavareddy. I have not conducted any class on Pathfinder on semiconductors. So yes, it will start from lecture 1. Obviously, it will be in Pathfinder only. Yep. Thank you, noob gamers. So this is very important, and 1 AMU is, because see, 12C means there will be 12 nuclear particles, neutrons, protons. So mass of one such particle on an average will be 1.66 into 10 to the power minus 27 kg. That's what 1 AMU stands for. You should know this. Very, very important. Yep. Yes, Shadow, I have released a video about JEE 2022 dates, and you should definitely watch it. Keep this in mind. Again, I'm repeating this. Mass of the proton is roughly equal to the mass of the neutron, which is roughly equal to 1 AMU. And this is much, much larger than the mass of an electron, or the electron's mass is negligible, hardly anything. Very good. This is how cool a nucleus looks like, but actually a nucleus is not even going to look like this. This is just a representation. Even those protons and neutrons are going to shake. They are going to move around. You cannot locate them so nicely. It's just a visual aid for you. But remember, this is not exactly how a nucleus looks like. Just like you thought electrons go around in orbits. But do you really think electrons just go around in orbits? No, right? It's a cloud of electrons. It's a probability density of electrons. It's how they, cover the nucleus. They have all sorts of probabilities everywhere, and each shell has different shape and size. So same way, even the nucleus is not exactly like this. It also has its own shapes, sizes, and you just represent it like this just for your understanding purposes. Very good. Next, let's talk about these three terms: isotope, bars, and tones. Very important, simple definitions. Sometimes questions do come on this. And yep, Gautam, very true. Heisenberg's uncertainty principle at play over there. So, one isotope, what is an isotope? Obviously, it's the same element, but it has different atomic mass numbers. So, like for example, hydrogen and this hydrogen, all of them have the same number of protons, but neutrons are different. So as such, chemically it is the same thing. The same element, just that the atomic mass number is different. So they are isotopes. So most of the elements around are going to have some or the other kinds of isotopes: carbon, oxygen, everything. Then isobars. Why isobars? What is isobar? Isobars are those atoms which have different chemical properties, but they have the same number of, nucleons. Nucleons, matlab protons plus neutrons. Imagine this. Hydrogen and helium, they are isobars. Their atomic mass numbers are same. So this is an isotope of hydrogen. This is also an isotope of helium, but they are isobars. Is that clear, my warriors? That upper number, if it is same, it is isobar. I hope this is clear. Even carbon 14 and nitrogen 14, that is also isobars. Perfecto. Bobby, bacha, leave a comment after the video. I'll definitely help you out. Okay. Shadow, I know, bacha, I've received a lot of flack saying that, how do you say that, sir, the dates are going to be in March? Guys, it's just a gut feeling. I always said that it's likely to be in March, but always remember, it's better to be prepared early than, imagine I tell you, no, the exam will happen in April. And by chance, let's say the exam gets announced in March. Then it will be a problem, right? Because you would have planned your timelines thinking that it is late, but if it is announced early, then it is a problem. It's better to be little bit optimistic about the dates. You can pull it little bit behind, so that even in the worst case scenario, even if it happens on that day, you are safe. But if it gets pushed ahead, it's good. For you, for me, we have more time to prepare. That's my only intention. I always think about you. That's how it is. Okay? Sugneshwar, I think I have just mentioned about the JEE dates, in the previous video. Just check it out. I announced it just 15-20 minutes back. Okay, next, isotones, they are nothing but of the same neutrons. Tone, N, neutrons. So same number of neutrons. So you can check this out. Lithium 7,3. So there are 4 neutrons because this is 3 protons. So the remaining 4 are neutrons. Then this one, 4 beryllium 8. So again 4 neutrons, and so on and so forth. Very good. So let's move on to some next part. I'm so glad you are happy about it, Shadow. Okay, KVPY Akash, it will, it's very doubtful, bacha. I mean, they act very weird. I mean, they decide randomly any date. They don't think about anything. So I really can't comment about KVPY. So worst case, it can happen in March, and better case, it will happen in May. Okay, that's what my expectations are. So the radius and the density of the nucleus. So a nucleus will also have its own size and volume and radius. So if you have a nucleus like this, which is made of protons, neutrons, like that. So the radius, what is the radius of the nucleus? The radius of any nucleus is always proportional to the number of nucleons is A raised to 1 by 3. So that becomes like this, R naught into A raised to 1 by 3. This is very important formula. Yep, very good, Ramya. Looks like you have learned a lot before the session. Very good, very good, very good. So what is the value of R naught? This R naught is 1.2 femtometers. If you are wondering what femto is, it is nothing but 10 to the power minus 15. Pico was 10 to the power minus 12. This is minus 15 meters. That's so small. Atom is of the size of Armstrong, 10 to the power minus 10. This is 10 to the power minus 15. It's crazily small, guys. 10 to the power 5 times small. Okay, that's something which you should know. Next important thing when we talk about the nucleus, that is the density. It's a very interesting thing to note. The density of the nucleus, which is mass divided by its volume, will be something like this. Mass. Okay, think about it. Mass of the nucleus will be the number of nuclear particles present. If you count it, it will be A into mass of each particle. So mass of each nucleon into the nuclear particles, that's A, divided by volume, that's 4 by 3 pi r cube, that's the sphere. Now I know what to do. R cube, the radius, I can use this relationship, put that 3 on the top. So 3 by 4 pi, and this will be mass of that nucleon, okay, into A, and R cube, right? So R cube means I have to cube this, so it will be R naught cube. A raised to 1 by 3 cube will be just A. Best part, AA gets cancelled, so that means it will be 3 times mass of the nucleons which are present divided by 4 pi R naught cube. Everything out here is a constant. This is one atomic mass unit, 4 by 3, R naught, all are constants. So this means the density is constant. So whether you take iron nucleus, gold nucleus, carbon nucleus, the density is the same, the radius is different. Yep, very good. No, it's femto. Okay, it's femtonevally. All right, very good, excellent. I just derived it. Viragava Reddy Kotapalli. Yep. What's the meaning of integrated MSc course? Just leave a comment after the session, bacha. I'll help you with that. Okay, so it's basically BSc plus MSc together. Okay, I think I've mentioned about density as well. Now let's see whether you can solve these questions coming up on your screen, and here it is. GSE, 2 elements pairs are given. SIS, 2 elements pairs are given. Are the examples of isotopes, isobars, isotones? You decide which ones are they. Okay, how many marks are needed to get into NIT Surathkal CSC? Well, MVR, there is a tool which Vedantu has. It helps you check the previous year, cutoffs for each category, for each state, because there are so many things I cannot remember. For EWS, for home state, for outside state, it will be different. For computer science, mechanical, it will be different. It's difficult to say, right on the top of my mind. There is a tool. You can just use that tool. You can just put in the marks and you will see all the cutoffs. If you are not able to find it, it's okay. Just leave a comment after the session ends. I will ping you or reply to your comment. Okay, Yuvasri saying B. Ramya, Sneha also saying B. Okay, looks like most of you are correct. Yep, it is. Isobars and isotones. What was isobar? Isobar meaning same number of protons or neutrons. No, it is the same number of nucleons. Keep this in mind. It was always the same number of nucleons. So you can see over here, the 76 and 76 is same. So basically nucleons means atomic mass number is same. Isotones. So when we talk about isotones, it's basically the number of neutrons. Neutrons means N, which is basically A minus Z. So you can check that out. 30 minus 14, 16. 32 minus 16 is also 16. So basically it has 16 number of neutrons each. So hence isotones. That's the correct answer. Next question coming up on your screen. Hi Shreyas Kapri, long time no see. How is everything? Very good Akash, very good Pharos, very good information text, Trinity, excelente. Next question, beautiful one, coming up on your screen. An unstable heavy nucleus at rest breaks into two nuclei which move away with velocities in the ratio 8:27. The ratio of the radii of the nucleus assumed to be spherical is how much? Come on, let's see how many of you can do this. Very interesting question. First, visualize it. It's mechanics plus nuclear physics combined. Trust me on that. Okay. Oh, Madhusudan asking, sir, were you worried, sad, angry? I was surprised that they pushed it so late. I was expecting CBSE to start the exam by April first week, and then NTA will be like, okay, let's chill. Let's conduct the first JEE Mains after CBSE, that too in May. Now that CBSE pushed it so late, April 26th, I was a bit of surprised. So now probably the NTA officials will wake up and they'll be like, oh wait, we need to make the question papers. Let's get ready. Hey, call everyone. Let's make question papers, gather everything. Oh, we don't have time. Okay, let's just copy the last year's paper. I don't know what they're going to do. Let's just hope for the best. All right. So unstable nucleus breaks into two halves. So what does it mean? So you have a nucleus something like this, and it breaks into two parts like this and like this. If this is M1 and this is M2, obviously this was M1 plus M2, right? They both go in opposite directions, and the speeds are in the ratio of 8:27. So let's say this is V2, this is V1. What is conserved? Momentum. It is screaming out there. Oh, I'm a mass, I split into two. Obviously momentum is conserved, just like it happens in explosion of bombs. So yes, conservation of momentum, just use it, you will get the answer. So let's see, conservation of momentum. So when I do that, initial momentum is 0, final momentum will be m2 v2 minus m1 v1. So therefore you can see, just take it around, you will see m1 by m2 will be v2 by v1. Now v1 by v2 is 8:27, so v2 by v1 will be 27 by 8. m1 by m2 masses will be proportional to atomic mass numbers, right? How many number of nuclear particles are there? And A's are proportional to, have you forgotten about it? Radius is proportional to cube root of A. Therefore A is proportional to R cube. Therefore A is proportional to R cube. Hence I get this as R1 by R2 whole cube, which is 27 by 8. Therefore R1 by R2 should be cube root of this. Perfect cubes out here. So 3 divided by 2, that is option A. Done, done, done. Excellent, Srinidhi. Yes, very good. So we have the tsunami of responses. Proud of you. Keep it up. Looks like you took my advice. Looks like you took my inspiration a little bit seriously, and I love it, guys. I love your responses. Keep it up. Is JEE first attempt after term 2? Chirag, Bacha, please everybody help him out. Help Chirag out. He is asking when are the dates. Guys, if you're true warriors, whenever somebody asks some questions like this, you should be like, hey, this video Shreyas sir has already made. Just check this playlist. Oh, check that. It's already there. Okay, yes, definitely MVR, definitely. Done, done, done. Moving on to the next concept. Oh, what do we have over here? Oh, we have a Pandu and he's wondering, what is he wondering? He's wondering if two protons repel each other. That's right. Then how do so many protons stay together in the nucleus? Perfect. Yes, he's worried about the right thing. Just like you guys are worried about when were the dates. Now Pandu is worrying about how do protons stay together inside the nucleus? They don't like each other. Makes sense, right? Very good. So here is the thing. See, nucleus has protons and neutrons. Proton, proton, positive, positive, they will repel. They won't like to be together. It's like two enemies being made to sit on the same bench. Has it happened to you in the school? You don't like someone. You hate someone. Like, oh, please don't stay away from me. And the teacher is like, hey, you sit with this person. And you are sitting like this. You're sitting like this. Has it happened? It has happened to me when I was back in school, of course. Okay. Anyways, so what about neutrons? Neutrons don't even have a charge. So they're like, yeah, fine, big deal. Yeah, you want to be here? Okay, fine. You want to be there? Okay, I have no issues electrically, but they will have issues nuclear wise. So there is a new kind of force called as the nuclear force, which overpowers the electrostatic force. Meaning, if you are sitting with a person who you don't like on the same bench and you're sitting like this, your friend is like, no, not your friend, sorry, somebody else sitting like this, you have some third person coming, hey, come on, stick together. The teacher, stick together. Come on, go close. So you need somebody to overpower that. That's your nuclear force. Perfecto. So nuclear forces are going to act between protons, between neutrons. They are not charge specific. They are a new kind of force like gravity, magnetic, electric. It's a very new kind of force. And I can see the tsunami of responses by all of you. Very good, Ramya. Very good, Sriniti, Nevli, Information Tech. Yep. And what happens is this force holds the particles inside the nucleus together. But they behave very weirdly. They don't have the same characteristics. Like you can see, the force is very strong. In fact, much stronger than electric force. And it is most of the times attractive. Repulsive is there certain times, but most of the times it is attractive in nature. It is not based on the charge, obviously, because it is not a charge-based force. It is not an electric force. It's a totally new kind of force. Just like electric force does not depend on mass. It depends on charge. Gravitational force does not depend on charge. It depends on mass. Nuclear force is a new kind of force. It depends on something else, which is the spin. So it depends on the spin of these particles. And it's basically a non-central force, as in it does not follow your inverse square laws. So F is Q1 Q2 by R square, KQ Q1 Q2 by R square, or G M1 M2 by R square. These are your central forces. Nuclear force does not have such a simple formula. Also, nuclear force is saturated force, meaning let's say for example you have two charges, they experience electrostatic force. You take them away, the force decreases and vanishes slowly. But nuclear, nah, completely different. You have two nuclear particles together, nuclear force. Move it away, okay, nuclear force. Move it away, gone, almost negligible, suddenly drops. So it's concentrated in a small region. So it is not like a gradual shift. That's what nuclear force is. It's a very short range force in the order of 10 to the power minus 15 meters, which is a femtometer. Yeah, keep this in mind. Got it? Have you understood all these pointers? Very important from both's point of view. If they ask you, write about nuclear forces, or in JEE Mains, or in VITSAT, or in CET, they can ask you a question based on this as well. Perfecto. Now I have a question for you. Here's the question. What's the question? Do you see this weighing machine? Do you see on one side what do I have? I have, hypothetical, imagine a massless weighing machine. I have helium nucleus. And on the other side, I have 2 protons, 2 neutrons. Which one do you think will be more? Which one do you think will be more? Let's see. Is helium nucleus heavier? Is 2 protons and 2 neutrons heavier? Or both will have the same weight? Think about it. What about others? Which one is more? Ramya is saying some kind of mass defect. Alright. Now I'll tell you what. You'll be like, helium, it has 2 protons and 2 neutrons. On this side, 2 protons, 2 neutrons. Yep. So it should be same. Yep. But it's surprisingly different. Now I'll tell you why it is different and who is more and who is less. Just stay tuned. For that, we need to understand something called as mass defect. Mass defect arises when the particles like protons and neutrons, they combine to form a nucleus. Their collective mass is completely different than the masses when they are weighed separately. Meaning, for example, okay, just say for example out here, you have 2 protons, okay, and you have 2 neutrons. This is separate. Okay, they are all independent. They are all independent. Now, let's say they are bound together in a nucleus. So now you have basically a helium nucleus. So you have those 2 protons and you have those 2 neutrons. Now, if you weigh this inside the nucleus, you will see that the masses when they were outside, basically independent, is more than when it is together. That difference which has arisen basically is called as the mass defect. That means some of the mass just got destroyed in this. It's very hard to believe, because you'll be like, sir, if you give me 3 pens, one weighs 1 kg, this weighs 1 kg, this also weighs 1 kg, 1 plus 1 plus 1 is 3. Now, if you bring them together, what's their total mass? You'll be like, obviously 3 kg. But no, in nucleus, it is 2.9 kg. You'll be like, oh my god, where did that 0.1 kg go? We're going to talk about it. But yes, you should know that the mass is slightly less. The mass is slightly less. So that difference of the mass is called as the mass defect. So usually I give this formula like this. So say for example, delta M will be equal to the mass of the nucleus, okay, and basically the mass of the independent nucleons. So I'll just put a modulus over there, so I don't even have to worry which one is more, which one is less. But yes, independent nucleons will always be more, because once they are together, it will become less. Okay, so this is the mass defect. Usually you express this mass defect in atomic mass unit. Very rarely you will express it in kg, because kg is a very large unit for these mass defects. These mass defects are extremely small. It's not like, oh, they combine and my god, 100 kg difference. No, it's very small. So that's why you express it in AMU. Yep. Yes, Lata, I have already mentioned about it in my video. Okay. Now, why does this mass defect arise? And where does this mass go? Einstein said, how many of you know this? Hi, Rashi. How many of you know what Einstein said regarding mass and energy, guys? He said that mass and energy are actually equivalent of each other. If you destroy mass, equivalent amount of energy is created. And if energy is destroyed, equivalent amount of mass is created. So, this is the generic principle of law of conservation of mass energy. So, this is called as the mass energy equivalence. Yeah, very interesting equation. You would have seen so many t-shirts, so many jokes, so many memes, so many, pictures on this particular equation, the most famous equation by Einstein. Although there are many more equations which Einstein gave, but this is peculiarly the most famous one. The mass can be converted into energy and energy can be converted into mass. And what is the relationship given between these these two things? It is nothing but the energy which could be released or which could be absorbed is delta M c square. So what is this delta M? This delta M is basically the mass which is either created or which is destroyed. Okay. In this case, this delta I is basically the energy. If mass is created, then energy would be destroyed. That means energy would be absorbed. So either it is the energy absorbed, or if mass is destroyed, energy is created or released. Okay, created or it is released. Okay, so this is the famous equation which you should know, because on one side you have joules, on the other side you have mass, and both of them are equivalent of each other when you multiply mass with c square. Beautiful equation. Just to give you a sense of this, imagine you have 1 kg. 1 kg mass, that 1 kilo that you have, imagine you destroy it. Guess how much energy you will get? C is 3 into 10 to the power 8, speed of light. Square, 10 to the power 16. 3 square, 9. 9 is very close to 10. 10 into 10 to the power 16, that's massive. 10 to the power 17, joules of energy. 1 kg of mass destruction gives you 10 to the power 17. So 1 and you have 17 zeros after that. That's what is the amount of energy just created by destroying 1 kg mass. Imagine how much energy you will get by destroying so many other masses. Crazy, right? Okay. Now let's talk about the next part. Okay, fine. We understood that when the particles of the nucleus are separate, they have more mass, and when they are together, they have less mass. The difference is called mass defect. That mass defect is related to energy. Fair enough. So how does that explain everything? Why is that difference there in the first place? Let's talk about it via something called as the binding energy. This is basically the energy associated with that mass defect. Very, very important. It's the energy associated with that mass defect, and that is called as the binding energy. So just to give an example, say, let's say you have, for example, 1 proton and you have 1 neutron, okay, and together it gives you a hydrogen isotope, okay. So basically it's an isotope of hydrogen, 1 proton and 1 neutron. Obviously the mass is slightly less here, this mass is more. So I can just mention over here, this mass is slightly more, okay, I can just put slightly more. This mass is basically slightly going to be less. Perfect. So where did that loss of mass go? That loss of mass, that mass which is lost, basically the defect of the mass, that gets converted into energy. The energy which is released out of this process. The energy which is released out of this process. That's how it comes. Is that understood? Now you'll be like, okay, so what? Why is this energy released? Why is it not absorbed? Okay, answer this simple question. If I am holding this pen, where do you think it wants to be? This pen, if I'm holding it, do you think it wants to be there? Obviously not, because if I leave my hand, it will fall down. Yep, it goes down. It wants to lower its energy. If you given a chance, you want to lie down, you want to fall down on the bed, you want to lower your energy. Everything in this universe wants to become stable by lowering its energy. Nothing in this universe wants to be highly energetic. Everything in the universe is lazy. Arya, I have already answered that in my previous video on this channel. Just check out the video which was launched just half an hour back. Just check it out. Okay. So basically, if that's the case, if everything in the universe is lazy, so I'm pretty sure that's something to be happy about, that you have company. You're not the only lazy ones out there. So guys, understand that, that laziness leads to this energy release, because the proton neutron have no reason to be together. But if you tell them, hey, you be together, and via nuclear forces, I will make sure that some energy is released, it's lost. You will lower your energy. They'll be like, okay, let's come together. That's what happens. Is that understood, my warriors? So this proton and neutron had no reason to be together unless and until their energy was lowered. So how is that energy lowered? By destroying a mass. That releases energy and that lowers their entire energy, and that's the reason why energy is released. That energy is called as the binding energy. Very, very important. Now, how is binding energy related? So basically that binding energy is basically the energy which is created or basically lost as per Einstein, and this will be delta mc square. Now usually, like I have told you, masses are never expressed in nuclear physics in terms of kg, because kg is a very large unit for it. Usually you express it in AMU. So if you express it in AMU, what happens is you need to convert kgs into AMU. Okay, convert that and substitute the value of C. When you do that, you will get a relationship, but that will be in joules, converted into electron volt. It so happens, it turns out to be delta M into 931 mega electron volt. Very important relationship. By heart it, remember it. How did this come? This came after the conversion of units. So substitute the value of C, convert joules to electron volt, and all of that, you will get it. Yes, Ramya, it is. Tushar, Vishnu, I think I just mentioned it at the beginning of the class. So I'm expecting NEET 2022 to be somewhere around June. And if my prediction comes through, I'll be very happy. So till now, my predictions all have been correct. So I'm really happy about it. Be it KVPY, be it your term 1, be it your last year examinations, be it your last year boards, last year JEE Mains attempts. So till now, I have been very close to what the actual things have been. So, yep, but you can still take my predictions with a pinch of salt, of course. Okay, now binding energy per nucleon. See, what is important is not just binding energy, it is binding energy per nucleon. I'll tell you why. Do you agree with one thing? Okay, do you agree with one thing that, you know, it's the amount of energy which is released which decides how stable that nucleus is. More energy released, lower the energy of the nucleus, more is the stability. But that's not what matters. What matters is the binding energy per nucleon. That means per particle. That is what is important. That decides the stability of the nucleus. Now I'll tell you how. Just imagine there are two people. One is Pandu, other one is Champa. Okay, this is Champa. Beautiful Champa out here. They both decide they are going to donate 100 rupees or whatever, some amount of rupees amongst all the beggars on the street. They decide to do some kind of social service. Okay, so now what happens is Pandu decides to give 1000 rupees to 10 beggars on the street. So how much did each beggar get? Each beggar got 100 rupees each. Makes sense? 100 rupees each. Champa, she decides, you are giving 1000, I will give 10,000 rupees. I will give 10,000 rupees. And she decides, I will give it to thousands of people. Fair enough, she gives it to 1000 beggars on the street. How much did each beggar get? Come on, answer it in the chat box. Each beggar got 10 rupees each. Although Champa spent a lot, gave it to many beggars, each beggar just got 10 rupees. But here, each beggar got 100 rupees. If I were a beggar, I would definitely be like, yeah, I would want the donations from Pandu, not Champa. Do you guys agree with that? Yeah, I would like to have the donations from Pandu, not Champa. Although Champa has been more generous than Pandu. That's what I'm saying over here. It's not the total energy which is released which matters, but the energy which is released per nucleon which matters. That's why that is the thing which decides the stability of the nucleus, not the total binding energy. Is that in your head? Is that understood, my warriors? Have you got the concept? Do let me know in the chat box. Hi Charan. Hence, binding energy per nucleon is binding energy upon the number of nucleons. As simple as that. Which is obviously, you can write it as delta M into 931 mega electron volt divided by that A. Nucleons is basically A, that capital A. Protons plus neutrons. Okay, so you can think of it that way. Very, very straightforward. Keep this in mind again. Alright, so I can also blog this for you, something which you should know. This one you have already seen. You usually express energies in electron volts for such small scales. Now what is interesting to note is that how the graph of binding energy per nucleon looks like with respect to different elements. And this has been already plotted. So right from hydrogen, nitrogen, sulfur, iron, you have uranium, molybdenum, all these elements have been plotted right over here, and you will see how much energy is there per nucleon which is released. Beautiful thing to note is that it is very low for hydrogen, and again it increases and then decreases for these elements, and it keeps decreasing for very, very heavy elements. That means, looking at this graph, which one is the most happy element out of all the elements, just by the names of the elements over here? Yep, come on. Hi Blessy, nice to see you. Little bit late, but you can catch up at 2x speed. Just go back even in a live class. You can do that anytime. Okay, which one is that element you think is the most happiest and stable element? Is it seen? Very good, Mohammad Rizwan. It is iron. Every element would like to be somewhere around this element because energy released per nucleon is the highest. This and this is not good. So a nucleus here will try to shift over here, correct? And a nucleus here will try to shift over here. But that's not so easy, my warriors. It's very, very difficult. Okay? It can happen sometimes naturally, sometimes it has to be forced. You cannot show this chart to hydrogen. Hey, look here. You can be very happy. You can reach here. Come on, be together. Hydrogen will be like, okay, fine. How to be together? It can't just combine together. It won't just come together and become iron. It would be funny if that would happen. Imagine hydrogen, helium, lithium suddenly deciding, oh, this chart is so nice. Let's all come together, guys. Let's fight for our rights. Let's become united and let's increase our binding energy per nucleon. All of them come together and become iron, and everywhere you have iron. That's not what is going to happen. No. Because there is electrostatic repulsion. Yes, the nuclear force is good, which will release that energy, but to overcome that, to reach there, you have to overcome the electrostatic force. There is a bouncer out there. Bouncer is like a guard, like a warrior, like a person standing outside the courtroom. It's like, hey, you need to cross me first. And that's the electrostatic force. Without me, or without crossing me, you cannot combine together. And electrostatic forces are pretty strong too. Only after they cross will the nuclear force become active. That's the problem. I hope that makes sense. So something which you get to know from this graph is that greater the binding energy, lesser is the total mass of the bound system, and greater is the stability. And stability is highest around here. These elements want to be here, these elements want to be here, but they can't overcome their electrostatic forces. But given a chance, obviously they would love to be together. Great. So this is some graph which you should know, and this was also asked in JEE examinations in different ways. First question coming up on your screen on this particular subtopic. The mass defect for a nucleus of helium is 0.0303 AMU. Binding energy per nucleon in mega electron volt is nearly. Yep. Yes, Srinidhi. Very good, very good. Let's solve this question, and here we have it. Binding energy per nucleon. And which kind of nucleus is that? That's helium. And for helium, what's the value of A? I know, that's 4, right? 2 protons, 2 neutrons. So what's the question? The question is binding energy per nucleon. So Be per nucleon is binding energy. What's the Oh, it's not given. Okay, so delta M into C squared divided by A. So delta M, that's 0.0303 into 931 mega electron volt divided by, do I have everything in? Yes, in MeV, yes, is nearly. A is nothing but 4. Okay, let me just shift the decimals. Okay, take this decimal here, and probably there are no decimals, so shift it here. 931.0. So that 0.0, that point you shifted by 2 units here and 2 units there to balance it out. So it'll look something like this: 3.03 into 9.31 divided by 4 MeV. Now you'll be like, why the hell did sir do something like this? Guys, I am a crazy teacher. What am I going to do? Just use some approximations. 9 3s are 27. So 3 point something, 9 point something will be obviously more than 27. Max value, what is more than 9? Or okay, think of it the other way. Something which is, 9 3s are 27, 9 4s are 36. Correct? So just think about that next multiple. It will be 36. It has to be less than 36, guarantee. Okay, because it's 9 point something and 3 point something. If you just shift one multiple, shift one number, the maximum value possible is 36. I know the numerator will be somewhere in between and divided by 4. Now guys, 7 4s are 28. So all the numbers over here, so like 32, okay, 32, and all these numbers are somewhere in the region of 7 and 8. That means, are there options close to 7 and 8? Yes, it is 7. Option B, correct. I hope this is understood what we just did over here. Okay, 7 4s are 28 and 8 4s are 32 and all of that. That's it. As simple as that. Just have to do some kind of simple approximation and manipulation. Don't have to sit and calculate it. Yes, that's correct. Moving on to the next one. BSc courses, no Tamizi Arzan, it is not. 2 deuterons undergo nuclear fusion to form a helium nucleus. Energy released in the process is how much? It's given. What is the binding energy for deuterium and helium? It's given. Let's try to figure this out. Deuterons undergo nuclear fusion to form helium. Okay. Binding energy per nucleon for deuteron is given. Deuteron and helium. Deuteron is nothing but an isotope of hydrogen. So basically, think of it this way, the proton and the neutron together gave hydrogen. All right. Over here, yep, 1 and you have 2. This is what it is, deuteron. And you got 1.1 mega electron volt. Fair enough? Next, helium. Helium will have 2 protons and 2 neutrons. Together gave you helium, nucleus, and it gave you, oh, wait a minute. This is per nucleon. How many nucleons are there? 2. So this will be 1.1 into 2. I hope you understood this because this is per nucleon. There are 2 nucleons, so into 2. That's the catch. Is that clear? Hi, Gagan. Okay, Akansha saying D for this. We'll figure it out. I don't know. Then here there are 4 nucleons. So 7 mega electron volt into 4. Do you understand why the 2 and 4 are there? Do you understand that, my warriors? Very good. Now think about the actual reaction. 2 deuterons, that means 2H1 plus, or rather into 2, gives you 1 helium nucleus. Interesting. How do I look at this equation? Think about it. If left hand side is causing the release of 2 into 1.1 mega electron volts, and the right hand side, when it comes from the same 2 protons and same 2 neutrons, causes the release of 7 into 4 mega electron volts. That means when the conversion happens from here to here, that energy difference will be the energy difference of these 2 numbers. These 2 numbers. Is that clear? Think about it. If 2 hydrogens combine into helium, and here I know 2 hydrogens require 2 protons, 2 neutrons, and 1 helium also requires 2 neutrons, 2 protons. So the products are different. That means the energy difference will be this energy difference. Which one is more? Obviously 7 4s are 28. So 7 into 4 minus 2 into 1.1. But remember, there are two such hydrogen atoms, so do not forget to multiply this as well with the 2. That is one catch. Many people forget this 2 over here. Remember, there are two such hydrogen atoms. For each hydrogen, this much energy is there. So for two such things, 2 into 1.1 into 2. So what will be the difference, guys? So 4 into 7. 4 is common because 2 2s are 4. 7 minus 1.1, of course, which is 4 into 5.9, which will give me, I think, 23.6. Just check this out. 23.6, because it will be 236. 59 into 4. Yep. I hope this is clear. Yes, that is the answer. That is the answer. No, Sachin, it is not option A. It will be option B. Be careful. 6 4s are 24. Okay. 6 4s are 24. So that 60 into 4 will be 240 because it is 5.9. So you have to subtract 4 from that. 59 into 4 will become 240 minus 4, which is 236. That's how you can get it. Okay. Is that clear, my warriors? Very good. So we have got the answer. Now moving to the next part. Next part is very interesting. This is all about radioactivity. We are slowly moving to the second half of the class, which talks about radioactivity. Remember this graph, which I just showed you over here. I told you these elements want to be here, these elements want to be here. Now when these elements want to be here, it cannot always happen naturally. Sometimes it happens naturally. Unnaturally means, you have to force it. You have to, somehow break it into pieces so that the heavy element becomes lighter. Sometimes it is so heavy, like uranium-238, it is going to naturally break into smaller parts and make it more and more stable. Make it more and more stable. Kajal, the JEE 2023 classes are already going on. I'm towards the end of the course. Watch the Nurture playlist. Nurture is for 11th standard, which is the 2023 class. So that's where radioactivity arises. And when the particles or when the elements, disintegrate and, they become more and more stable, you will see apart from the new nucleus being formed, they also emit some more radiations, some more particles. So we are going to talk about that as well as the nuclear reactions. So the three most important particles which occur when an element breaks or elements combine are basically these alpha particles, beta particles and gamma particles. Alpha are very big, beta is decent, gamma is like a photon. Alpha and beta can hardly pass through thick sheets, but gamma can pierce through many things. Many things. So coming back, elements which are unstable or even they are naturally unstable or unnaturally, you have to break them apart. When these elements break into smaller pieces to become more stable, or let's say these elements are forced in together to become more stable, you will see the release of certain particles. They are called as alpha, beta, gamma particles. Alpha is the big one, beta is the smaller one, gamma is the smallest. Now alpha, strictly speaking, is nothing but a doubly ionized helium nucleus. So 2 positive charges plus 2e, atomic mass unit 4 AMU. That's it. It's a doubly ionized helium. Beta is nothing but a negative charge. It's nothing but an electron. And similarly, gamma is nothing but a photon, which is nothing but light. It's light of very high frequency. Gamma is very high frequency, even more than X-rays. In that electromagnetic spectrum, after ultraviolet and all of that, you get basically your X-rays. After X-rays, you will get gamma rays. Very energetic. That's the reason why they can pierce through so many things. So, coming back, what is alpha? Okay, what is alpha? So alpha particle is nothing but doubly ionized helium nucleus. So I can say it is helium doubly positive nucleus. So think about it, mass wise it is roughly 4 AMU. Charge wise it will be plus 2E. That's what an alpha particle is. It's a big one. But what about a beta particle? A beta particle is nothing but an electron. It's nothing but an electron. The mass is very, very small, 10 to the power minus 31 kg. In terms of AMU, it's very small. But charge-wise, we know it is minus E. Okay. Now, the last particle which I was telling you, that is your gamma particle. Gamma is nothing but a photon of very high energy. It's a very high energetic photon. Remember, photons don't have mass. So the mass is not even defined. The rest mass is assumed to be 0. I hope this is clear. And next thing, charge. Well, obviously, photons don't even have any charge. Keep this in mind. They are nothing but electromagnetic waves or electromagnetic radiation. Keep this in mind. Now, there is one more particle called as a positron. Usually this beta is also referred as beta minus or electron because it is negatively charged. The twin brother of an electron is called as a positron. It has similar properties, but a small difference, beta plus. That is nothing but called as a positron. That is also emitted certain times. The mass, everything is the same. Mass is also 10 to the power minus 31 kg and all of that. The only difference is the charge is going to be plus E. The charge is going to be plus E. Okay, Sanjit Krishna, looks like you're seeing me after a very long time. Glad you're back and be very regular now. Can you crack JEE mains in 2 months? Yes, working for 16 hours. Definitely MVR, keep up that spirit. Can wave pass through mirror or prism? Well, yes. X-rays and highly energetic rays can even pass through mirrors. Mirrors can reflect your normal light, but for high frequency waves, they can even pass through mirrors as well, Abhishek. Okay, so Lakhiruam Lanchembi, where can you find electronic? What is the meaning of electronics? There is nothing like electronics. Do you mean semiconductors or do you mean electrostatics or do you mean current electricity? Please be very specific. Or do you mean AC circuits? All of these are electrics. So be more specific so that I can guide you. Okay, coming back. So when an alpha particle is emitted, alpha means doubly ionized helium. That means 2 protons, 2 neutrons. Then the element which will decay, which will split, and it has thrown out alpha particle, then the remainder will be a new element because think about it, the atomic number will have to reduce by 2 because 2 protons have gone. So very, very important. All of this is basically coming because of loss of 2 protons. The atomic mass number will reduce by 4 because loss of 2 protons and 2 neutrons. That's the reason why atomic mass number reduces by 4. And X prime, that's a completely new element. This is also known as the daughter element. And you can call this like the parent element. That's what it is called. Okay. Semiconductor, I'll be doing it day after tomorrow. Lakshmi, Laikuram Lanchenbi. Okay, so I'm so sorry I'm not able to pronounce your name, but I hope you get it. Day after tomorrow I'll be doing it, and it will be probably divided into 2 classes. One just semiconductors and PN junction, and the next class will be transistors, logic gates and all of that. Okay, similarly over here guys, you can see this is a completely new element. Z plus 1 because a beta particle is 1 electron. So minus 1, you should always be able to conserve the equation. So if this is Z, on the right hand side also when you add all the lower subscripts, it should add up to Z. So here, you will see atomic number increases. It increases. Reason for that, can you guess? A neutron splits into a proton and electron. So that's because a neutron will split into a proton and an electron. That electron goes out, that proton stays inside the nucleus. So that's why, you know, the atomic mass number does not change because the neutron just converted into a proton. So A will remain the same, but you will see the electron goes out. That's what happens. Very good. Next up, gamma. Now, oh, by the way, before going ahead, this X prime is also different. This is different. It's a new element. It's a new element. You can see this is X prime, this is X. For gamma, it's a very surprising thing. X star and X, are they different or same? The answer is both of them are same. The symbols might look a little bit different. This over here just means that it is excited. This is basically the same element. And photon does not have charge, does not have mass, so 0, 0. So AZ and AZ balanced the equation. It has balanced the equation right over here. You'll be wondering, sir, what has just happened? I mean, like, it's the same thing here, and why, what is this 0, 0 gamma coming out? I'll tell you what. See, do you remember in atomic structure, electrons go around the nucleus, correct? And when the electron jumps from higher orbit to lower orbit, what happens? When the electron jumps from high to low orbit, what happens? A photon is emitted, correct? And when the electron jumps from high to low orbit, does the atomic number change? Does the element change? Does the neutrons change? No, right? It's the same element. It's just that it was excited, now it got de-excited. Fair enough. Now, a nucleus also has orbitals, also has different energy levels. This is just an excited nucleus. Excited nucleus. This excited nucleus just became de-excited. It's the same protons, same neutrons, just in a different energy state. That's the reason why the difference of that energy goes into the energy of the photon. As simple as that. Hi Khadija Naushain. Yep. Do radio waves emit alpha, beta or gamma? No, Abhishek. Radio waves is a lower version of gamma rays. Alpha and beta, they are particles, protons, electrons. Gamma is a photon, light. Light can have different wavelengths. Radio waves, gamma rays, X-rays, ultraviolet, red, yellow, infrared. So radio waves is very large wavelength, gamma rays is very short wavelength. That's the difference. Is that clear? Okay. I'm so glad, Neville as Jude, that you are helping out all the new warriors who are joining the channel. Okay. Now there are certain more characteristics which you should know from board's perspective. I have just put it up for all of you, like the ionizing power for alpha particle is very high but very low in penetration. Beta being small, okay, it can penetrate little bit more than alpha, and the ionizing power is decently okay. Gamma, although they are very small but they are very high energy, so that's why they can pass through many things but hardly any ionizing power because of their size. So something which you should know. Okay, so let's move on. Now, yeah, let me just drink some water. Yes, Abhishek, they are, but we don't study them in nuclear physics for JEE or NEET as such. Yes, Daya, yes, bacha, it will be. It's like a topper batch. Yep, it is. So if you are joining the Vedantu, or if you are in Vedantu in 11th standard, then students, based on their test performances and their attendances and how they have performed in their benchmark test, all the results combined together, there will be a separate batch formed. Yep, it is. Okay, now what is nuclear fusion? Like the name suggests, fuse. Fuse means join. Two nucleus combined together. That is called as fusion. Today only I was just listening to the BBC News, and they said that the scientists have created a fusion reactor which is like a mini sun. In the sun, hydrogen nuclei combine together at very high energy to form the helium nucleus. that creates tremendous amount of energy. So that nuclear fuel is there in the sun, and that's how our sun is so bright and gives out all the energy and the heat and light and all those things. But if you can create a miniature version of the sun, that will solve all our energy problems. So you don't have to depend on wind, you don't have to depend on coal, you don't have to depend on petrol. So it's a crazy form of energy. A lot of research is going on fusion reactors, which can act like, almost like an infinite source of energy, and it will be crazy. It's also said China has created the mini sun. Elon Musk had even more crazy ideas. He's like, okay, let's just create one more sun and let that mini sun orbit the Earth. And that sun will have some nuclear fuel, and it will be based on the nuclear fusion. That's crazy idea. Many people obviously didn't like that idea. Like, come on, even I don't like it. In the night time, imagine Elon Musk's sun is revolving around the Earth, and I'm like, I just want to sleep, man. Let me just sleep. I just don't want that light around. I just want to be at peace. I don't like that light in the night. Please. I don't know how many of you agree with me. Okay. Yes. So I'm hoping that some of you at least agree, and some of you at least want to sleep peacefully in the night and don't want the second and third sun. Imagine 5 suns. Yeah, crazy, right? Anyways, so a nuclear fusion is where the nuclei combine to give a big nucleus and a lot of energy is released. The exact opposite is fission, breaking apart. So, I'm so happy, Yash. I'm so glad that you got enrolled. I'm hoping I'll be seeing you soon. Hi, Snehita Kongari. And yes, I can see a lot of you agreeing with it. Night will be called day, day will be called day. There is no night. If you want night, I don't know what you should do. Nuclear fusion, fission is where it breaks. Look at this. Neutron bombardment, this explodes, new particles, fragments, these are daughters. So that's what fission is. Breaking into smaller fragments, breaking it apart, cutting it. That is fission, cut. That is what fission is. Very good. Okay. Telugu Radu Vivek. Neevu Cheppandi. Okay, Vivek. Now Radu. All right. Okay. So usually nuclear fission can be forced. Sometimes it is natural. Forced meaning you bombard it and you break it, like breaking a bottle by throwing a stone. Sometimes it is unstable by itself, so it's basically going to degrade naturally. It was never stable, like some relationships. Yeah, you might have seen some movies like this was never going to work out. Yeah, so we broke up. So that was bound to happen. That is natural fission. That is because of radioactivity. Those are called as radioactive nuclei. But some nuclei are happy. Some third party comes in, some villain comes in between the hero and the heroine, and he breaks that relationship. So that is artificial, forced fission, forced breakup. Okay. Yes, Vivek, I do. Oh my God. Somebody saying in our class also relationship broken. Was it radioactive? Was it forced? Who was that neutron? Okay. So, great. Let's move on. Sudarshan, hi. Yes, sun's core, natural activity. Yep, it is. Slow neutron. Sachin saying, oh my God, a slow neutron? Crazy, Sachin. Okay, so what is this Q value? This Q value tells you how much energy was lost or gained in any fission or fusion reaction. As simple as that. Okay, so that's what the Q value is. It's basically the amount of energy which is associated in any fission or fusion reaction. So Q, if it is positive, that means exothermic. Okay, if Q is negative, that means endothermic, energy was absorbed. As simple as that. Okay, very cool. Q value, keep this in mind. What is Q value? So any reaction happens, nuclear, fusion, fission, doesn't matter. I'll just give you an example. Say, we have some reaction like this. A plus B is equal to A plus B. Something happened, I don't know, some crazy reaction. Here the masses are different, here the masses are different. So delta M will be basically the mass of, look at it, difference between the sum of the initial reactants, that means mass of A plus mass of B minus mass of A plus mass of B. That will give you delta M. From this delta M, you can find a delta E. This will be delta M C square. This delta E is called as your Q value. Okay, as simple as that. Sure, Sudarshan, I am planning to grow it like Pushpa, and I'm hoping to crack that dialogue one day, just like Alu sir does. The delay. Okay, one day. Okay, come on, let's do this. Next question coming up on your screen. The radiation suffering the maximum deflection in a magnetic field is which one? Which one? Which one is it? The radiation suffering the maximum deflection in a magnetic field. Magnetic field, what does it do? Does it affect the charges? Yes, it does. Which chapter discusses that? Oh yes, magnetic, magnetic effects of current. Remember that QV cross B? Okay, we are going to miss after 12th crops. Abhishek, what are you going to miss after 12th? I'm not sure what was the context. I probably lost that context. Okay guys, very simple. Let's go over here. Remember, F is a Q, V cross B. This X-rays, no charge. Gamma, no charge. So why will it even deflect? Okay. Alpha, plus 2 charge. Beta, minus 1 charge. Minus 1E, this is plus 2E. You'll be like, sir, the charge is more, force is more, deflection is more. Guys, you forgot one thing. Acceleration is force by mass. So for the deflection, what you need is not just the force, but also the acceleration. I hope this is clear. That means, think about it. If you compare alpha and beta, who has more mass? Obviously alpha has lot of mass. So even if the force is more, the mass is so much more that force can't compensate. Hence, that acceleration will be low for alpha particle. Acceleration will be very low for alpha particle. So alpha will hardly deflect. Beta will have lot of acceleration and more deflection. Hence, the correct answer is beta, in spite of beta having smaller charge. I hope this is understood, bacha. Oh, yep, very good, all my amazing warriors. Okay, now moving on to the next one. In the given reaction, okay, something AXX is going to give you AYX plus 1 is going to give you KA minus 4K X minus 1 is going to give you KA minus 4X minus 1. Radioactive radiations are emitted in the sequence. Which radiations are emitted? Think about it. I'll put a question mark here, here and here. Okay, think about it. Okay, it's not about binding energy, Jay. It is the mass. If the mass of the product is more, mass of the reactant is less, that means more mass has been gained. How will you get more mass? By destroying energy. That's why you will see that the Q value will be negative. Is that clear? Okay, perfect. Yes, this type of question is tough. No, it is not tough. I'll tell you why. See, look at what has changed, what has not changed. In the first part, A is the same. X has increased. Atomic number has increased. Where does atomic number increase? Go back to this slide in case you have forgotten. I just told this to you. Atomic number increases in beta decay. Atomic number decreases in alpha decay. In gamma, nothing happens. So now this will help you solve this question. Let's go over here. Yep. So here atomic number has increased. That means beta particle has come first. Next, here the atomic mass number decreased. Atomic number also decreased by 2. That only happens in alpha decay. So remember, in beta, what happens? There is +1 increase in the bottom, no increase or change on the top. In alpha, it decreases by 4 and decreases by 2 at the top and bottom. And then last one, it's the same thing. So it has to be gamma because there is no change whatsoever. Hence, the answer is a beta, alpha, gamma. No, it is not D, it is B. It is how mass and velocity related. As in like Abhishek, in what context? Like mass into velocity is momentum, but anything else, like in what terms are you talking about, Abhishek? I'm not so sure. Okay, beta, alpha, gamma. Let's move on to the next one. I hope Jai Ajinkya, your doubts are clear, bacha. Can we go ahead? No problems. Happens, flame, hope, YT. That's why you are here to learn. Which of the following are not examples of nuclear fusion? Are not examples of nuclear fusion. Look at the options, you will get it very easily. Again, go from here. Formation of helium from hydrogen. Obviously, it is a fusion reaction. It is a fusion. Hydrogens combine to get into helium. Formation of water from hydrogen and oxygen. Hydrogen, oxygen becomes H2O. Combines. Okay. Well, technically, this is also not fusion because, you know, it's a chemical reaction. It's not nuclear fusion. So this is also, you know, a lot of people think that this is nuclear fusion, but actually this is not a nuclear fusion. Think about it. Nuclei are not combining. Hydrogen plus oxygen gives you H2O. It's not the nucleus, it's the bonds which are being formed. So it is not a nuclear reaction. I hope this is clear. Next, formation of deuterium from hydrogen. This is a nuclear reaction because when you have hydrogen and, you know, it is like this, it is like this, and it then becomes like this. It has added one neutron. So the neutron has entered the nucleus. So this is a nuclear fusion reaction. A, formation of barium, Ba and Kr from U-235. This is basically the fission reaction. These are smaller elements, Ba and Kr. They are smaller elements. So basically that is a fission reaction. So this is not fusion. So which of the following are not examples of fusion? It will be option A as well as option C. Both options will be correct. Okay, both options will be correct. I need to correct this by, putting it right over here. So don't worry, I'll get it corrected in the PDF. Is that understood? Neither this nor this. Everyone? Okay, Aryan, the messages are not automatically getting deleted. It is basically you are only retracting it. You are only deleting it. Okay. Okay, great. So fusion YB by nucleon of the heavier nuclear is more than the BE per nucleon of the lighter nuclear as the mass of the heavier nuclear is more as compared to. So Aryan, it's not as simple as saying it has more mass, so it will release more energy, because these binding energies per nucleon also depends on how well the protons are getting bonded. It depends on the nuclear forces, neutron, proton, neutron, neutron, proton, proton interactions. That's why these nuclear forces determine binding energy per nucleon. So it's not just related to mass, more energy. No, it's not like that. Okay. So mass and velocity are inversely related if momentum is conserved, Abhishek. Okay. Is that okay, bacha? Okay, let's move to the next question. The binding energy of A and B are E and EB. 3 atoms of B fuse together 1 atom of A. So the question is, what is EA, EB and Q's relationship? So let's see this. 3 atoms of B. 3 atoms of B gives rise to 1 element, 1 atom of A, and when any reaction happens, the energy which is associated with it is given by the Q value. Remember that? It's given by the Q value. Now, in order to have 3 elements of B, what you will release is 3 times the binding energy of B. For making 1 element B, 1 atom of B, you will need EB amount of energy which will be released. So for 3b atoms, you will need 3 EB energy. Makes sense? Okay, great. Or no, Aryan, that's not the case. Okay, next, A will have how much energy associated with it? It's already mentioned, it is EA, is the energy or binding energy associated with the element A. Now, if you look at these, if you rather convert the masses into energies, things become very simple. Look at this, what will be the value of Q? Q will be the difference of these two, which will be 3EB minus EA. 3EB minus EA, because 3EB plus EA, because 3EB which is equal to EA plus Q. So Q will be 3EB minus EA. Is such option there somewhere? Option B, I suppose. Yep, it is. Clear, my bacha? I'm so glad, Aryan, Abhishek, your doubts are cleared. Okay. अगर डिसोसिएशन हो रहा है, डिसोसिएशन क्यों होगा? It's not about that, Narayan Datta. It's okay. Think about it this way. Okay. See, when you have small nucleus, the protons, neutron interaction is very good. Okay. Now, to make it more stable, you need more binding particles. Neutrons act like binders. So when more neutrons comes and for the more protons, it becomes more stable. So till a point, the atoms become stable because more binders, more neutrons are coming into the picture to hold the protons together. But after a point, if you just keep on making the element heavy, addition of these neutrons and protons will make no sense, because the neutrons, protons have become so many in number that they can hardly interact with the other neutrons. Although many neutrons are there, it's like you entering a big party. There is no point, you can hardly talk to few people around you. What's the point of having 100 people or 1000 people? You are going, at the end of the day, you are going to talk to 10 people around you. So that is the problem. So that's the reason why after a point, the binding energy per nucleon decreases, because the stability decreases. And there is no point of adding more neutrons and binders out there. I hope this is clear. Okay, let's move on to the next one. Yep, let's go to the last part of this chapter, and that is called as the radioactive decay. Very important and very interesting topic as well. So, I just told you that a radioactive nucleus, is unstable and it decays. It gives a daughter nucleus and some of these particles like alpha, beta and gamma. Now, when this happens naturally, there is a beautiful law which is obeyed. And that law is called as the law of radioactivity. What does that law say? It says that, let's say you have some amount of radioactive sample. Okay, so this is basically your radioactive sample. Okay, this is, let's say, at some time instant t. That radioactive sample will be decaying. Obviously, it will be decay and it will be emitting radiations. Okay, so it will be emitting radiations, and you will see as it decays, those active nuclei will become inactive because it will become more stable. All right, so probably it will become, the number of radioactive elements or the number of radioactive atoms in that sample will decrease. So as soon as the radiation happens, you will see fewer number of radioactive elements present over here, and most of it would have now converted into inactive samples. So maybe I'll show it in some other color. Okay, these elements basically they have already decayed. Is that clear? So let's say initially that sample had n number of nuclei, n number of radioactive nuclei. After some time, t plus dt, let's say, or t plus delta t, let's say the number of decayed were dn in number. So how much is remaining basically? How much is remaining? N minus dn remaining. They are the remaining radioactive sample. Now, what was found experimentally? What was found experimentally is very interesting. I'm so glad, Jai Ajinkya, that's my whole aim, bacha. Let's do this. What was found experimentally is the rate of decay is directly proportional to the number of radioactive sample present at that particular point of time. This is exactly the law of radioactive decay. So if you write it mathematically in terms, rate of decay, rate at which it disintegrates, how much disintegrated, how much decayed, rate of decay means dn is the amount decayed per unit time. So that's why dn by dt is proportional to the number of sample present at that time, which is nothing but n, but it is decay. That means it is reducing. So if 5 atoms are going off per second, that means this should be a negative value. So it is minus n. And now I put the constant of proportionality. So it will be minus into lambda n. This is something which you should know. What is this lambda? This is obviously called as the decay constant of that radioactive material. So essentially every element has a different rate of decay. Uranium different, thorium different, everything will have different lambda because they have different nuclear properties. That's what it is. I'm so glad, Aryan, my micro courses have helped you. My favorite chapter of 12th standard physics, that would be electromagnetism, of course. Sir, can we watch the recorded sessions in the Vedantu's crash courses? Yes, not just Vedantu's crash course, any course you take, you can watch the recordings till the last exam. Okay. Okay, very good, very good. Oh my god, Anarya also loves electromagnetism. Hi Vijay Anand. Hello, how are you guys? Okay, hi Lata M. Nice to see all of you. I'm so happy, guys. We are reaching almost the end of Pathfinder. And yep, don't worry, semiconductors is still there. I'm going to have 2 classes. Guys, you know, I was thinking, you know, when I was deciding today, should I have 1 class of semiconductor, big one, or 2 classes? So, because it's a decently big chapter, not too big. So then I thought maybe I should conduct it in 2 sessions. 1 session where we talk about what is these energy levels and semiconductors, intrinsic, extrinsic, and what's a PN junction and a diode and all of that. And another class just dedicated for transistors and, you know, electronic devices and like logic gates and all of that. So I'm going to split it up in 2 parts. The second lecture will be a little bit short, of course. The first one is going to be very, very, you know, intensive and intense, I would say. Okay. Neville is saying we are going to start the next series. Oh yes, of course. I have already planned. My Excel sheet is already full of all the lectures for the entire month. I have planned it already. Don't worry. Okay, so let's do this. So what do we have next? I can rearrange this. At the moment I see derivatives, I don't like it. I mean, come on, you are in 12th grade now. The moment you see some dx, dy, dz, you're like, sir, let's integrate, sir, let's integrate. I don't like this d. Obviously, let's start integration. You should blindly start the moment you see d's. Let's just rearrange, get it in a beautiful form. Shift that n below over here. dn by n will be equal to minus lambda dt. Now integrate. Tongue. Limits. What are the limits? When time is 0, the number of elements were n naught. Initial number of elements. When the time is t, the elements are n. dn by n's integration, 1 by x's integration is log of x. So this will be ln n from n naught to n minus lambda, and dt's integration, that's t of course from 0 to t. Okay, I am not sure if I have enough space, but it's very obvious. This will be ln n by n naught. Log a minus log b is log a by b. Come on. This will be minus a lambda t minus 0, which is t. Fair enough, just rearrange guys, you are going to get n is equal to n naught e to the power minus lambda t. That's a very important equation. Please understand this n naught over here stands for the initial amount. The initial amount. Okay, keep this in mind. N naught. Okay. I'm not sure about that, Latha. Maybe we should ask Wasim sir. What am I going to do after Pathfinder ends? Is it the sprint series? Yes, we will have some kind of sprints, but it's obviously going to be more of problem solving sessions and strategy sessions for all of you. So after the syllabus completion, there's no point doing the same thing again and again doing the theory part. It's useless. So different kinds of problem solving sessions, different kinds of strategies, what you should do, what should be the timeline, which books you should do, how do you do the mock test, how you should analyze your papers. So these kind of sessions will also be there, plus a lot of problem solving sessions, advanced sessions, mock tests, all of these things are going to be there. Okay, so the number of nuclei I just gave you. Oh, there is a minus sign out there. I don't know why it was not present out here, so let me just put it. Okay, lambda is the decay constant. Fair enough. Now let's talk about the next part, which is activity. So activity is basically the rate of disintegration or the rate of decay. So the amount which is getting decayed per unit time is called as the activity, and clearly by the definition, activity is nothing but just dN by dt, number getting disintegrated per unit time. Now dN by dt, I just told you dN by dt is nothing but minus lambda n, and n, I just told you, it is nothing but n naught e to the power minus lambda t. Interesting. Now from this I immediately understand one more thing. Observe this. Very interesting. I don't know whether you can see it. This part over here, this lambda n naught, guess what that is? Lambda n naught. Just like lambda n is a, lambda n is minus lambda n is a. What will this be? Think about it. This will be nothing but just initial activity. Lambda into initial number will give you initial activity. Does that make sense? Very good. Very good. Excellent. And this will be a, and this will be e raised to minus lambda t. Very good. So this is a very similar equation, just like the n's equation. N is n naught e to the power minus lambda t. Very, very similar. So beautiful equation which you should remember. And there are different units of activity, something which is standard is there in the textbook, becquerel and Curie. So 1 becquerel is the standard unit. So 1 becquerel is when 1 disintegration happens for 1 second. 1 Curie is when you have 3.7 into 10 to the power 11 disintegrations per second. These are standard things which you should remember. Jay, if your syllabus is on the verge of completion, then how will crash course help you? Well, crash course lectures will help you in problem solving, and I would suggest don't watch the crash course videos in order. You can choose which videos you want to watch. Don't have to go sequentially. Okay, you are weak at rotation, watch rotation first. Don't have to go in order, number 1. Number 2, assignments. Directly after watching those lectures, go with the assignments. Those chapters where you are confident about, just solve the assignments straight away. If you get stuck, that means you need more knowledge, then watch the videos. That's how you can do. And once you are decently confident, let's say about 70 or 80% of the syllabus, then start attempting the mock tests. Before that, you can even attempt the part mock test when you complete part of the syllabus. So that's how you can use it. Okay, let's solve some questions based on this. Radioactive sample at any instant has disintegration rate of this much per minute. After 5 minutes, the disintegration rate is this much per minute. Then the decay constant is how much? Let's solve this question. Per minute, that means what is given? Per minute disintegration rate. This is nothing but your activity. Activity. And I just gave you the formula for activity. Activity is equal to A naught e to the power minus lambda t. Rearranging it further, because I can see all the answers in logarithms, I think I need to rearrange it. So A by A naught is equal to e raised to minus lambda t. So log of A by A naught is nothing but minus lambda t. Okay. minus sign this side. So log of A naught by A is equal to lambda T. Next, log of A naught by A. Initial is 5000, final is 1250. So basically log of 5000 divided by 1250. Okay, 1250 in how much time? In a time of 5 minutes, I guess somewhere it is given. Yes, 5 minutes. So lambda into 5. So this 0 goes, and this will be how many times? 4 times. So log of 4 is 2 log 2 is equal to lambda into 5. So lambda will be 2 by 5 log 2. 2 by 5 because all the answers are in decimals. That's 0.4. So 0.4 log 2 is equal to lambda. Do I have such answer somewhere? Yep, I have it. Option A, 0.4 log 2. Is that clear? Yep. Well, I teach carbon dating. Okay, I'll tell you what carbon dating is, Aryan Singh. It's simple. Actually, we are too early for talking about carbon dating. Oh my god, it's not even Valentine's, Aryan. We should talk about carbon dating on Valentine's Day. Okay, anyways. One student also asked me, sir, how miserable my life is. Even carbon can date. I can't find a date, sir. Just imagine, sir. Carbon is like one black thing, carbon. Even that is able to find a date. My life is so bad, sir. So sad. I can't find a date. Bad. So I just told him, listen, simple reason why you're not finding a date. Carbon, C14, is radioactive. You're not radioactive. That's the reason. So you become radioactive. That's how you're going to find a date. Okay, anyways, a very bad one though. How many people are laughing? Oh, we have 3 kids laughing. I'm so happy. All right. So what do we have over here? Carbon dating. Carbon dating, what happens is human body also has radioactive elements. Radioactive elements. And there is a small proportion of it. When you're alive, the C14 radioactive isotope keeps getting replenished. If it gets flushed out of your body, so when you visit the toilet, it gets flushed out. So it also automatically comes back into your body because you obviously eat. Now, when you die, obviously you don't eat, you don't go to the toilet. So that radioactive sample inside your body just keeps on getting decayed. So what they do, you know the standard amount which should be present inside an alive human being. Let's say it is this. You know what is the current radioactive level in the dead human being? Let's say it is this. If you know the lambda, that is this lambda out here, by this formula you can find the time after the death. Yep. No, sorry, not the date, the death. Oh my god, 2 crazy things, 2 opposite things. Yeah. Very good. Is that clear, my warriors? Understood though? Clear? Oh? Yeah, so that's how carbon dating works. So it is based on the activity which is there presently and the activity which should be there in a normal human being. You compare it using that formula, as simple as that. Perfect. Moving on to the next one, half-life, midlife crisis. So what is this midlife, half-life? It's the amount of time which a radioactive sample takes to become exactly half its initial value. So the sample initially was like this, it keeps on decaying, it becomes half, the amount of time it takes to become exactly half of it. And that's not pretty difficult because if you use this formula, n is equal to n naught e to the power minus lambda t, if n becomes n naught by 2, n naught goes, so half is equal to e to the power minus lambda t, flip it, so it will become, or just bring this down, so 1 by 2 is equal to 1 by e to the power lambda t, so 2 is equal to e to the power lambda t, so log of 2 is equal to lambda t, therefore t is equal to log of 2 by lambda. So I just got the formula. It's simple maths. So the half-life of any element is a log of 2 by lambda. Very, very interesting formula. Log of 2, you should know the approx value. What is the approx value? 0.693. 0.693. Keep this in mind. Okay, yes. Very good. Moving on to the next part, average life. Now, basically, each element will stay alive for certain time. Example, you have let's say 1, 2, 3, like that. You have n radioactive elements. They are all radioactive. This element, let's say it remained and then it decayed. This element remained here and then it decayed. This remained till here and it decayed. So each element will have different amounts after which it will get decayed. This is your timeline. This element got decayed here. So each one will have different times, T1, T2, T3, Tn. So the meaning of average life, where all these points are the points where it gets decayed. Okay, then the average of that is called as the average life. As simple as that. So average life is just T1 plus T2 plus Tn divided by n. That's your average life which stays alive. Abhishek, yes, CBSE term 2 announced long time back. I just went live at 7 o'clock. There's a reason why I conducted my class starting from 7:30. Please watch the video, bacha. Okay, and what is the average value? You will be like, some kids are like, sir, what is this triangle out here? Okay, this angle brackets. So usually when you use the angle brackets, it means average or mean. Okay, very good. So, yep, there you go. This value comes out to be 1 by lambda. Something which you should know. You should also remember this from your first order kinetics reaction from chemistry. Yep, first order kinetic reaction, half-life, average life, you would have done all of this. Yeah, right, very good. So remember this. Let's start solving some questions coming up on your screen now. Half-life of a radioactive element which has only 1 by 32 of its original mass left after a lapse of 60 days is how much? Are you going to use some equation? If it is, which one it is? If not, what are you going to do? Half-life of a radioactive element which has only 1/32th of its original mass left. Interesting. So if it had something, let's say n, after one half-life, it becomes n by 2. After one more half-life, it becomes n by 2 by 2, which is n by 4. Again, one more half-life, it becomes n by 4 by 2, which is n by 8. One more half-life, oh my god, n by 16, and one more half-life. I hope this is the end. Yes, that's n by 32. Think now. Count. Everybody start counting. How many half-lives? One half-life, second half-life, third half-life, 4 half-life, 5 half-lives. 5 half-lives to become 1/32th of the original mass. So the time will be 5 times of T half, and what's the time? 60 days. What is T half? T half is 60 by 5, which is 12 days. Do I have such an option? Yes, I have. Done. Very good, Ramya. Excelente. Perfecto. Amazingo. There we go. No need of any formulas, just pure logic. 1 by 32, you know it is the power of 2. 2 raised to 5 is 32. That's it. That should click in your mind that yes, after 2 raised to 5, that means after 5 half-lives, it will become 1 by 32th. So 5 half-lives is 60 days. So 1 half-life will be 60 by 5, which is 12 days. Great. Moving on to the next one coming up on your screen. Tabu, welcome. Okay, there we go. Thank you, Narayana. Two radioactive materials X1 and X2 have decay constant 10 lambda and lambda respectively. Initially, they have same number of nuclei. Ratio of the number of nuclei of X1 to X2 will be 1 by E after how much time? Okay, let's understand what is happening. Say, X1 and X2 have decay constants this and this. Initially, they have the same number of nuclei, N0 and N0. Let's say this is X1, I suppose, and this is X2. Both of them decay. This has 10 lambda, this has lambda. After some time, this will have N1 nuclei, this will have N2 nuclei. This ratio is coming out to be 1 by E. The question is after how much time? That's simple, I'll tell you how. Just take the ratio. N1 by N2 according to the question is 1 by E. N1 by formula is N0 into e to the power minus lambda is 10 lambda into t. N2 by formula, wow, we have a butterfly. So N0 into e to the power minus lambda t, because for the second reaction, decay constant is lambda. This is 1 by e. N naught goes, bring this guy down, so it will become 1 by e to the power minus lambda t into e to the power 10 lambda t is equal to 1 by e. I don't like everything down, I bring it up, so it will become e over here. Okay, I can add the powers, right? 10 lambda t minus lambda t, that's 9 lambda t, so this will become e raised to 9 lambda t. Fair enough. Compare the powers. Oh my god, this is 1 actually. So basically 9 lambda t is equal to 1, but what did we want? We wanted the time. Okay, so time will be 1 by 9 lambda. And do I have it somewhere? Yes, I have it. Option D. Yep. Hello, welcome everyone. Yes, there you go. That's the answer. And here is your homework question coming up on your screen. Yes, Janet, Johnny. Very good, Ankit. Enjoying the questions. Hello, Khanshar. So there we go. This is your first homework question. This is your second homework question. This is your third homework question. This is your fourth homework question. Assignments given to you. Fifth homework question. You can take screenshots of all of this. And the crash course. That's also your homework. Please take it up. Syllabus is about to be over. Now you need to take up the crash courses so that, and it's available for 8,000 bucks, guys, because you need the practice test, you need the assignments. Although I will be doing everything on as much as possible on YouTube. If you want that extra push, you want that personal care, you want the doubt solving, you want the test papers with the report cards, you need to go ahead with the crash course. So I'll tell you how you can go ahead with it. It's very simple though. All you need to do is just visit this website. Well, you're already there on the YouTube channel, of course. So where are we? Am I there somewhere? Yes, there I am. I'm live. And just go down and just go to JEE Crash Course. Click on this link. Just select obviously your class 12, JEE 2022. But if you want the CBSE term 2 crash course, that's also available. Click on this. There you go. You will get this in English medium. Course starts 7th Feb. That's recent. If you want, you can even go back here so that your course ends before. It's the same thing. You'll get all the recordings, doubt solving, best teachers, all live sessions plus the recordings. The validity is till the last JEE exam, whichever is the last, however extended it gets. It now says 9,000, but when you actually go to buy now and use my coupon code, you will get extra off only when you use this coupon code SHCC or SHHPRO. Keep this in mind. Okay, my warriors, that's how you join it. Excellent. So I hope you guys are enjoying these sessions. So yes, there is discount. You will get extra 1,000 off out there. Just try it out. Okay, great. And nuclear sizes are usually expressed in femtometer, not Armstrong. Armstrong is very big for nucleus. Yeah, okay. Baba Jeevan, Baba Jagdish, Baba Sriniti, Baba Janet, Ashish, Narayan, Bhavani, Ramya. Take care, Skull, Baba Ankit, Baba Divya. Good night, take care and stay safe, stay healthy. See you in the crash courses, see you in YouTube as well, because a lot of questions, a lot of sessions also being planned for all of you out here. So stay tuned, hit the like and the subscribe button, share it with your friends, get more crowd on our channel. We need you, all right? Only with your Josh, your love and support we can grow, and that's how we can conduct more sessions for you on YouTube. Bye-bye, take care. Hasta la vista.